Mars, our enigmatic red neighbor, has captivated humanity for centuries, and its two small moons, Phobos and Deimos, are no exception. These peculiar celestial bodies stand out for their unusual characteristics. They are small, irregularly shaped, and orbit Mars in nearly perfect circular paths aligned with the planet's equator. But how did these moons come to exist? This question has puzzled scientists for decades. At first glance, Phobos and Deimos resemble captured asteroids, given their size and lumpy shapes. However, captured objects usually follow erratic orbits, often elongated or tilted, which makes their circular, equatorial paths around Mars a significant anomaly. Another long-standing theory suggests they may have formed from debris caused by a massive impact on Mars, much like Earth's moon. Yet, this explanation struggles to account for the stark differences in their altitudes and how far Deimos sits from the Martian surface. The lack of a definitive answer has left scientists grappling for a better explanation. Could there be another mechanism at play? In recent years, a groundbreaking hypothesis has emerged, one that suggests these moons may have been born from the wreckage of a colossal asteroid torn apart by Mars' gravity. This idea, tested through advanced computer simulations, has opened a new chapter in the search for answers. Stay with us as we unravel the mystery behind Phobos and Deimos, explore this intriguing new hypothesis, and uncover the exciting ways science is poised to solve one of Mars' oldest riddles. Phobos and Deimos have long perplexed astronomers because they defy simple categorization. Their peculiarities have spurred competing theories over the years, yet none fully explain their existence. Let's start with the first and perhaps most intuitive idea, that Mars moons are captured asteroids. At a glance, their irregular shapes and small sizes make this explanation plausible. However, their orbital behavior tells a very different story. Captured moons typically exhibit chaotic orbits, elliptical, inclined, or even retrograde. For instance, Neptune's moon Triton orbits in the opposite direction of the planet's rotation, a clear hallmark of capture. In stark contrast, Phobos and Deimos move in nearly perfect circular orbits that align precisely with Mars' equatorial plane. Such precision suggests a different origin, one where these moons formed in situ rather than being dragged into orbit. The second major hypothesis borrows from Earth's own history, a massive impact on Mars that ejected debris into space, which then coalesced into Phobos and Deimos. This is similar to the widely accepted model for how Earth's moon formed. At first, this seems like a reasonable explanation, especially given Mars' history of colossal impacts. But when scientists simulate this scenario, a problem arises. Phobos and Deimos occupy vastly different altitudes. Phobos orbits just 6,000 kilometers above Mars' surface, while Deimos is 23,000 kilometers away. Models struggle to explain how debris from the same impact event could form two moons with such striking differences in distance. These challenges have left both theories with critical gaps. The asteroid capture model fails to explain their orderly orbits, while the impact hypothesis falters in addressing their spatial distribution. This impasse has pushed scientists to seek a third explanation, one that could bridge the divide between these inconsistencies. That's where a bold new theory steps in, suggesting that the moons were born from a dramatic event in Mars' gravitational grip. Rather than a planet-wide collision or random capture, what if Phobos and Deimos emerged from the disintegration of an asteroid that ventured too close to Mars? This fresh perspective rewrites the narrative, combining elements of both chaos and order in a way that finally makes sense of these mysterious moons. In the next part, we'll delve into this fascinating hypothesis and explore how cutting-edge simulations have brought us closer to understanding the origins of Phobos and Deimos. Stay tuned as we uncover the science behind this groundbreaking model. What if Mars didn't capture its moons, nor did they emerge from a planetary impact? A groundbreaking theory suggests that Phobos and Deimos were born from the destruction of a wandering asteroid, an event that merged chaos with cosmic precision. Imagine a massive asteroid on a collision course with Mars. As it approached the planet, it crossed a critical boundary known as the Roche limit. At this distance, the tidal forces exerted by Mars' gravity became stronger than the asteroid's own ability to hold itself together. The result? The asteroid was ripped apart, its fragments scattered into orbit around Mars. Using advanced computer simulations, a team led by Jacob Kagaris at NASA's Ames Research Center explored this scenario. They tested hundreds of variables, such as the asteroid's size, velocity, rotation, and how close it came to Mars. These simulations revealed that in many cases, enough debris survived the initial destruction to form a dense, orbiting disk around the planet. Over time, collisions among the fragments ground them into smaller particles, which eventually coalesced to form Phobos and Deimos. What makes this model particularly compelling is its ability to address the unanswered questions from previous theories. The orderly, circular orbits of the moons align naturally with the dynamics of material forming from a debris disk. Furthermore, the model explains how Deimos, despite being much farther from Mars, could have formed in the outer regions of the disk, while Phobos emerged closer to the planet. This hypothesis also highlights a fascinating efficiency. The asteroid that gave rise to these moons could have been significantly smaller than previously thought. According to Jack Liesauer, another scientist involved in the study, the key lies in the disk's ability to distribute debris to the right places, ensuring there was enough material for both moons to form. However, as promising as this model is, it remains a hypothesis for now. The true test lies in the evidence, and the answer may come from Phobos itself. In just a few years, the Japanese Aerospace Exploration Agency, JAXA, will launch the Martian Moons Exploration (MMX) mission, a daring project to collect and return samples from Phobos to Earth. These samples could hold the chemical clues needed to confirm or refute this bold new theory. But the implications don't stop with Mars. This model could be adapted to understand similar events across the solar system, from the formation of Saturn's rings to the origins of other puzzling moons. The destruction of a single asteroid may have left a legacy that shaped not just Mars but the broader history of planetary evolution. In the next part, we'll explore how the MMX mission could unlock these mysteries and what secrets Phobos might reveal about its past and the history of Mars. The journey into the unknown is just beginning. As theories evolve and simulations refine our understanding of Mars' moons, the true test of any hypothesis lies in the evidence. That's where the Martian Moons Exploration (MMX) mission comes into play, a groundbreaking project that could rewrite the story of Phobos and Deimos. Led by the Japanese Aerospace Exploration Agency, JAXA, the MMX mission is set to launch in 2026 with an ambitious goal: to land on Phobos, collect samples of its surface, and return them to Earth for analysis. This daring venture promises to provide the first direct evidence of the moon's origins, offering answers to questions that have baffled scientists for decades. One of the key tools aboard MMX is MEGANE, a sophisticated instrument provided by NASA. Short for Mars Moon Exploration with Gamma Rays and Neutron Experiment, MEGANE will map the chemical composition of Phobos with incredible precision. By identifying the elements present on its surface, MEGANE will help researchers determine whether the moon's material matches that of Mars itself, supporting the impact hypothesis, or if its composition is more akin to an asteroid, lending weight to the new Roche limit model. The stakes are high. If Phobos and Deimos contain traces of Martian rocks, it would suggest they formed from debris blasted into orbit by a massive impact. On the other hand, a chemical signature resembling that of an asteroid could confirm that these moons are the remnants of a celestial body destroyed by Mars' gravity. This discovery would not only solve the mystery of their origins but also deepen our understanding of how moons form around planets across the solar system. But the MMX mission is about more than just Phobos and Deimos. It represents a significant leap forward in planetary science and exploration technology. The mission's ability to land, collect samples, and return them safely to Earth will pave the way for future endeavors to study other celestial bodies. Moreover, the techniques used to analyze Phobos material could be applied to a wide range of planetary systems, from Saturn's enigmatic moons to the distant icy worlds of the Kuiper Belt. Beyond the science, the MMX mission also captures the spirit of international collaboration. With contributions from JAXA, NASA, and other global partners, it reflects humanity's shared curiosity about the universe and our collective drive to seek answers to its most profound mysteries. As we await the mission's launch and eventual return, the anticipation grows. Phobos holds the key to unraveling not only its own history but also the broader story of Mars' evolution. It may even provide insights into the early solar system, when chaotic collisions and gravitational forces shaped the planets and their moons. In the final part, we'll explore the potential impact of these discoveries on our understanding of Mars, the solar system, and the very nature of celestial dynamics. What secrets will Phobos reveal, and how will they reshape our cosmic perspective? The journey to uncover the truth is only beginning. Phobos and Deimos, once overlooked as mere oddities, may now hold the key to understanding the forces that shaped Mars and the solar system. If the MMX mission confirms that these moons were born from the disintegration of an asteroid, it will redefine how we think about planetary formation and the interplay between gravity, collisions, and cosmic debris. This discovery would also provide a fascinating glimpse into the early solar system, a time when planets and moons were still forming amidst violent interactions. Mars, with its thin atmosphere and surface scarred by ancient impacts, serves as a living record of these primordial events. By studying its moons, we could unlock secrets not only about the red planet but also about Earth's own early history and the processes that created the worlds we know today. The implications extend far beyond Mars. The same principles explored in this new model could apply to other moons, like Saturn's enigmatic Titan or Neptune's Triton, and even to structures like the rings of Saturn. The story of Phobos and Deimos is a reminder that the universe is a tapestry of interconnected phenomena, where the destruction of one object can give rise to the creation of another. As humanity continues its exploration of space, missions like MMX highlight the incredible potential of combining advanced technology with human curiosity. They remind us that every answer we uncover leads to new questions, deepening our understanding of the cosmos. So, what will Phobos reveal? Will it confirm its origins as the fragment of a wandering asteroid, torn apart by Mars' gravity? Or will it surprise us yet again with an unexpected twist? The answers lie on its surface, waiting to be uncovered by MMX's intrepid journey. As we stand on the brink of this groundbreaking mission, it's an exciting time to be curious about the universe. Stay connected to the latest discoveries and scientific breakthroughs, because each one brings us closer to understanding the grand design of our solar system. Subscribe, follow, and join the journey as we continue to explore the mysteries of space, one moon at a time. Together, we'll unravel the secrets of the cosmos.